Okay, we might have lost the first half of the lesson, but I don't think anything that was vital. Okay, keep going here. There are actually 6 trig ratios. You guys should be familiar with at least 3 of them, though. One of the ratios is sine, and sine is basically opposite over hypotenuse, right? Well, you might not have known this, but there's actually a doppelganger to sine called cosine. No, cosecant. Here it is. You know how it's opposite over hypotenuse? Well, all you're going to do is flip it upside down and make it hypotenuse over opposite. We rarely use these ones. They're not all that purposeful. But there's actually like a doppelganger here where all you do is you flip the ratio. Rather than it being so, it's like, rather than O over H, it's H over O. That's all. You just flip it upside down. Cosine has a doppelganger called secant, where you flip A over H to being H over A. And tan has a doppelganger called cotan. Grade 11s, that's actually not your curriculum. Okay, so I'm going to show you it now just because you will eventually learn it, but this is actually one of those times where I'm cheating a little bit. So just so you guys know, in grade 11, this is not really something you're supposed to know how to do, but honestly, it's super easy. Okay, I promise you, working with these other 3 ratios is actually quite simple. Okay? And why don't I skip ahead and I will do this example right here. Here's a basic triangle. I'd like us to find all 6 trigonometric ratios. Let's do the easy 3 first, the one you know. So SOHCAHTOA. SOHCAHTOA. Okay, sine is opposite over hypotenuse. Hang on a sec, what's the opposite? If this is my angle right here, what's the opposite side? Can we find it though? Using? Perfect. Pythagoras' theorem, right? So if this is the hypotenuse, because it's the side across from the right angle, right? If this is 4, hopefully I'm not going way too fast by saying c squared is a squared plus b squared. 11 squared equals 4 squared plus b squared. 121 minus 16 is b squared, so it's the square root of 105. Didn't do that way too fast for you guys to follow. Okay, we now have all 3 sides. One side is 11, the other side is 4, and the remaining side is root 105. Okay, so let's try finding the 6 trig ratios. Sine of my angle would be the opposite over the hypotenuse. It's not hard. What would cosine be? Cosine would be the adjacent over the hypotenuse. Tan would be the opposite over the adjacent. You guys okay with that so far? One of the things that I showed you at the end of last day then is that if you want to solve for that angle, you could use any of these to solve for the angle. All 3 should work. Okay. If I were to inverse sine root 105 over 11, I should get an angle of 68 degrees and change. But I didn't have to just use sine. I could have used cosine. If I inverse cosine 4 over 11, that's not going to work. 4 over 11. So I get the exact same answer. And if that wasn't sufficient enough for you, I could have even inversed tan. Don't do it twice. Root 105 over 4. And I still get the same answer. Does that make sense? Okay, well, there's actually 3 more identities that I want to teach you about. The 3 extra ones, they're known as the reciprocals. You guys remember reciprocals from either the previous unit you might have done or at some point in your life? A reciprocal basically means to take the fraction and flip it upside down. So if it was 8 over 1, it's now 1 over 8. All you do here then is you just have to know which one is which. Sine's doppelganger is known as cosecant, and it just means you make it 11 over root 105. That's it. Which is why I don't mind showing it to you guys in grade 11, because all you have to do is just take whatever the fraction was and flip it upside down. That's it. Is that reasonable? So like I know I'm showing you something that's not actually a curriculum, but it's not actually that much harder. Cosine has a doppelganger known as secant. What would secant be equivalent to then? Yeah, just flip it and make it 11 over 4. And tan has a doppelganger known as cotan. All you do is you make it 4 over root 105. That's it. They might rationalize, though. You guys remember rationalizing? It's where, like, if there's a root on the bottom, you would times by root 1 over 5 over root 105. Just to save time today, I'm not going to bother doing that. But these are known as the 6 trig ratios. Now, in theory, you would think, well, why doesn't your calculator have these buttons on them? Well, the reason why is, well, why bother? All you got to do, if I ever give you a cosecant, all you've got to do is just flip the ratio upside down, and then just use sine. Does that make sense? So to save time and space, rather than having all 6 of them be known, most of the time we just use these ones. And if you ever need to use these guys right here, all you have to do is flip the ratio upside down, and then rather than using cosecant, use sine. Rebecca. You know how in permutations we did something like 6 pick 3? Or sorry, this is 3 pick 2. There are 3 sides to a triangle, and I want to pick 2 of them to make a ratio. 3 pick 2 is 6. But 3 choose 2 is 3. Essentially what I'm saying here is if order doesn't matter, if we don't care about which one we use for flipping it, most of the time we do this. But in theory, we could have flipped these 2 and had like the opposite one, I guess. Just because it exists, I guess. But like most of the time, we only work with just these 3, and we say, well, why bother counting these 3? Because isn't it literally the same thing? You kind of get where I'm going with the 3 pick 2, 3 choose 2. Is if it really, 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 truly mattered, the order, then you'd want to have this one, this one, this one, this one, this one, and this one, because there's 6 ways of having 3 sides and taking 2 of them. But most of the time, we just work with those ones because that's all that we really need. I don't know if that really fully answers your question, but like these other 3, we don't use them a lot because why bother using them? Why not just use these ones instead? Okay, so now what I want to do is try to combine some of the skills we've been working on here, and I've already kind of shown you this. If we take a triangle and plot it onto a coordinate grid, we can more or less do the same thing if something is in standard position. The only things that change are we can now calculate this point right here. And I showed you guys real quick an example of this before I ran out of time last day. But like this coordinate point as an xy value can actually help us find different angles in a triangle. And all we need to know is whatever this point is right here. So I already did some future examples. A few more things I got to talk about though. Just for like, so that we're all using the same vocabulary. Rather than using A, B, and C, you know how we sometimes use like A, B, and C as the 3 sides of the triangle? We don't use that anymore. We now use X because it literally is on an X grid. Rather than using B for another side of the triangle, we use Y. And then the other side we use is R. I don't think I wrote on this slide what R is for. So does someone want to take a guess as to what R stands for? Nice, radius, yeah. Because the idea basically is that as you go around a circle, this distance right here is like a radius, just like the sun going around. So you may see, rather than using a squared plus b squared equals c squared, you might start to see things that say x squared plus y squared equals r squared. It's still Pythagoras' theorem, it's just we're using different letters now. Does that make sense? What we might also end up seeing then is that rather than writing these things as opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, if we're going to label an angle like this with this being x, this being y, and this being r, we might actually see them labeled as y over r, x over r, and y over x. Because really, y is your old opposite from this angle here, x is your adjacent, and r is your hypotenuse. Okay. Now this doesn't really impact you all that much. I'm just saying if you see x's and y's and r's, just keep in mind x, y, and r are what used to be opposite, adjacent, and hypotenuse. Does that make sense? So why don't I hop through now and try, we did this example last day, right? Why don't we try this one here? So we're trying kind of merging some skills together. Again, I'm not really doing anything purposeful yet. I'm just trying to like build some soft skills. So that when we eventually do want to try to accomplish something really worthwhile in solving trig equations, you have a little more experience with this. So here's what I'm going to ask you to do. We're going to plot the point -3, -8 as though it's part of the terminal arm of an angle in standard position. So where would -3, -8 lie? Somewhere about here. This is -3, -8. Is everybody okay with that part so far? Okay. Well, if I were to plot this then, this right here to this right here is kind of how I should be plotting my angle. The angle that we're looking for then is basically going all the way around like that, right? Remember, as it clockwise goes around the circle, if I were to ask you to estimate the angle in degrees, you want to take a stab at how many degrees you think that is? How many degrees all the way around to about there? Give or 250. Yeah, that's actually what I had in my mind, 250. My rationale is I know that straight down would be 270, because that's the third multiple of 90. So it's a little bit less. Where's the reference angle, though? Is this the reference angle? No, the reference angle has been defined as always going to the x-axis. So if I were to make a triangle out of it, look something like this. Here is a triangle, and there's a little reference angle sitting inside there. That makes sense? Okay, if I wanted to label a little bit more, I actually could. This side right here is the adjacent side, but it's actually now the x value. This side right here is -3 units, because it's going backwards 3 units, right? This side right here would have been the opposite side on the triangle. Now it's actually the y value, it's -8. What's the radius of this thing? How do I solve it? Pythagoras' theorem. Okay, so -3 squared plus -8 squared is the radius squared. 9 plus 64 is the radius squared. 73 is the radius squared, so root 73. That's right there. You follow that? Okay. Let's write out our 6 ratios. We'll start simple with the ones we're familiar with. So sine. Sine used to be opposite over hypotenuse. But in a system kind of like this, where we're plotting it on a grid, it's no longer opposite and hypotenuse so much as it is x and r, or y and r. Does that make sense? So the opposite to this little reference angle right here would be the -8, which was the y value. So it's going to be -8. And then what used to be the hypotenuse is now the radius, and the radius is root 73. So there, that's what sine of theta would be equal to. What about cosine? Well, cosine of theta is what used to be the adjacent, only the adjacent in this triangle right here is our x value, so it's -3, and our hypotenuse is the radius now, which is root 73. And then tan is opposite over adjacent, so opposite over adjacent, y over x. I know they were both negatives listed right here. Can you guys understand why I didn't bother writing the negatives here, though? If you do -8 divided by -3, you don't need the negatives anymore because it's not positive. Okay, in case you're wondering, that is grade 11 curriculum. Okay. Here's the grade 12 curriculum, but I'm going to show you grade 11s anyways because that's honestly not that hard. If I want you to write the other 3 ratios, it works like this. Cosecant is root 73 over -8. secant is root 73 over negative 3. Sorry, it's messy. Tan, cotan becomes 3 over 8. That's it. Does that make sense? So that's why I felt like I may as well just show the grade 11s while we're doing this right now anyways. Because it's like one step further. Literally all you got to do is just memorize 3 new symbols here. And all you do is you flip the fraction upside down. To what point? Honestly, there isn't really much point. That's actually why we never use those other 3. Why would you use a cosecant when you can just flip it upside down and use a sine? Does that make sense? So I don't know if that maybe answers your question, Rebecca, but like we don't use these other 3. If we ever had to, we'd just flip them upside down and use the other one. Does that make sense? Okay. Okay. One of the things you might then hear is something called a unit circle. Did I go too fast? Do you want me to flip back? Sorry, should I go back here again? You're good? Okay, so you threw your hands up. I wonder. Okay, I'll move on then. You guys may hear something called a unit circle. If you ever hear the phrase a unit circle, what it means then is that the radius is 1 unit. Okay. Now, this is actually just there's one little change. What was the radius right in this last example right here? Well, the radius was root 73. If you want to make this a unit circle, all you have to do is make it so the radius was 1 instead. Let me show you how to do this. It's actually really simple. Let's say that your triangle was supposed to be, I'm going to redraw it here. Where was it? It was negative 3, negative 8, and root 73. Is the radius 1? No. So I just want to make the radius equal to 1. Here's how I do that. I downscale it. How do I turn root 73 into the number 1? Yep, that's it. Good job. Which means, though, that if I'm going to divide this by root 73, I have to divide everything by root 73. So it now means that this is root 73, and this is root 73, and this guy right here is now 1. Okay, so if you ever come across the phrase unit circle, which grade 11s, I'm not putting that on you yet, but you will, okay, like next year. So I'm looking mostly at grade 12s. All you got to do is take whatever the radius is and divide it by itself. Now it's 1. Just make sure you divide everything by it. Okay? Which means then that this point in the corner here has now been moved. This point in the corner is now at negative 3 over root 73, comma negative 8 over root 73. That's all. Everything has now gotten root 73 times smaller, but now you can call it a unit circle. That's all. Is that easy enough? I want you to look at one more thing here. I went back a slide, not forward, by the way. Negative 3 over root 73. Negative 8 over root 73. I feel like those are familiar. It's actually one of the reasons why we talk about unit circles, is that when you find sine and cosine are actually the x and y parts. You know, like when you plot like an x and a y coordinate point, if you find whatever sine is, it's actually the y coordinate if it was on a unit circle. Because remember, how did we make it a unit circle? We just divided everything by, in this example, root 73. Right? Well, isn't sine just that number divided by root 73? Isn't cosine just that number divided by root 73? So in a way, what I'm trying to show you here is that this xy point right here, if it has to be a unit circle, it's actually really easy to find. The x coordinate is the cosine of your angle, and the y coordinate is actually the sine of your angle. Let me show you that one more time, so you can kind of, hopefully you'll agree with me on this. Remember how, in order to make this a unit circle, I divided everything by the radius. The radius was root 73. So it used to be 3, 8, and root 73. It's now 1, root 3 over 73, 8 over 73, right? So this is my x and my y point right here. The point I was trying to make is that, boy, those sure looked familiar, right? Didn't I just see them a minute ago? Right? Well, where did I find these guys a minute ago? I found them right here. the y value is actually whatever sine of theta is equal to, and the x value is actually whatever cosine of theta is equal to. So what I'm trying to show you here is this interplay of how we can work with triangles, but we can also put them on a grid, and the point on the grid right here is something we can talk about. Again, we're not quite ready to do a whole lot with it yet. That's our next lesson. So, any questions on that? Oh. Okay. Another thing you might find useful as we're kind of building skills up to like my whole point of this 3-lesson climax here is to try to figure out where some of the ratios are positive and negative. You guys might have noticed on you stay on this slide, okay? But I'll flip back. You guys might have noticed that in this quadrant right here, did you notice how sine was now a negative ratio and cosine was now a negative ratio? And the reason why they were negative numbers is because we're going backwards and we're going down. Does that make sense? Well, depending on which quadrant we're in, some values will be positive, but some values will be negative. Like, for example, as I go forward here, let's say that we put something in this quadrant right here. And I ask you to find that point right there. Which values will be positive and negative? Well, isn't this going to be a positive number right here? Isn't this going to be a positive number right here? And isn't the hypotenuse going to be a positive number right here? So if I do this divide by this, or this divide by this, or this divide by this, whichever ratio I try to divide them by, I'm always dividing positive numbers, right? So that means that regardless of whether we're looking for sine, cosine, tan, cosecant, or whatever, hopefully you'd agree, isn't everything going to be positive in this quadrant? However, that's not always the case. What if we were to, I'll put in another color here, what if we were to go in this quadrant right here? Well, in this quadrant right here, when we use a coordinate point, the x and the y, the x is negative. Because isn't the x going backwards? And then the y goes up? And so if that makes sense, didn't I just show you a second ago that the x really refers to cosine and the y really refers to sine? What this means here then is that sine is going to be positive, but cosine is actually going to give you a negative value. And because of that, what I'm going to tell you here is that anything in this quadrant right here that is sine will be positive in this quadrant here. But cosine stuff will be negative. Because isn't cosine equal to your, like, say, adjacent over your hypotenuse? Isn't this adjacent right here going to be negative? Won't that make it a negative value? Even tan. Tan is opposite over adjacent. But isn't your adjacent negative? So you'll get a negative value. So it means that sine is positive in this quadrant, but that's it. Well, you can use that same logic. I'll do the other two quadrants just for the sake of showing you these. But there's actually an acronym that someone came up with. They call it the cast rule. And it works like this. Cosine is always positive down here. That's the C for cast. Everybody, all people are positive in this quadrant. Sine is positive in this quadrant. And the one we haven't talked about yet is actually tan. Tan is positive in this quadrant. Let me show you why tan's positive over here. We actually were just in this quadrant right here. See how sine was negative when we were down here in this quadrant? Because this was a negative number, and that was positive. Cosine was negative because this was negative, and that was positive. Why is tan positive, though? Because two negatives make a positive, yeah. So what ends up happening is if you're in this quadrant over here, tan is actually positive. And then I'll show you this last one here. Here's cosine. If I were to put any point in this quadrant right here, and I call it x and y, hopefully you'd agree, though, doesn't the y have to be negative? Because the y is the one that's going down. Now, again, I showed you this a few minutes ago, but x is really whatever the cosine of theta is equal to, and y is whatever the sine of theta is equal to. Well, sine of theta is a negative number. Why is sine of theta a negative number? Well, sine is supposed to be opposite over hypotenuse. If this is your reference angle right here, here's your opposite right here. Isn't your opposite going to be negative? But cosine won't be. Cosine is supposed to be adjacent over hypotenuse. This is your adjacent on this side right here. Is your adjacent negative? No, it's going in the positive direction. So this is a clever little acronym that can help you figure out which quadrants will give you positives and negatives. We call it CAST. The only thing you have to remember, though, is that you're actually not starting in quadrant 1. I know that quadrant 1 is normally where we start, but when you write out the CAST rule, you actually have to start C-A-S-T over there. So that's what this slide right here is all about. You gotta go. Just take it. Okay, we are now getting to the point where I finally taught you kind of enough stuff to put together that we can start to solve one of our first questions. Is this my last slide, by the way? Okay. If I can, if you guys are still up for it, I'd like to finally merge into my final topic. Everything we've done up until now is finally culminated in this and what I'm going to do in our last lesson, which is we now want to try to solve trigonomical equations. Okay? And hopefully you'd agree as you look at this here, we kind of have been given a trigonomic equation. It's right here. This. And we're being asked to solve and do some work with this. So I'd like to take this piece by piece because there's actually a lot of information here. The first thing it tells me is that cosine of theta is 4 over 5. Now, this actually means two things. Isn't 4, if we're talking cosine, isn't the top number of cosine supposed to be the, say, adjacent? And isn't the bottom number supposed to be the hypotenuse? Well, I could plot that right here. Think about that right here. I could make the adjacent side be 4, and I could make the hypotenuse side right here be 5. Doesn't that seem to fit the parameters? Cosine of theta is 4 over 5. I need an adjacent side to be 4, which is the x value, and I need the hypotenuse side to be 5. However, here's one of the things we're going to start working on. There's actually more than one place that this triangle could go. Do you guys remember the phrase coterminal angles? Not only can you go around the circle multiple times or go backwards around the circle multiple times, but I can actually put this in a different quadrant. I can actually write the exact same triangle in this quadrant down here. Because watch, I still am going to have a hypotenuse of 5, and I'm still going to have an adjacent of 4. Okay. Just a few seconds ago, I told you guys about this cast rule. I'm going to write it out here. The way the cast rule works is it goes C-A-S-T. Where could cosine give me a positive value? Well, there's actually two locations. Cosine can actually be positive if you're in this quadrant right here, because everybody's positive there. But I can actually write a ratio, and I can plot a triangle on this graph right here, and cosine is still positive. Does anybody know what the remaining side is? Because, I mean, one side is 5, the other side is 4. What's the other side? That's 3 if you don't know. Use Pythagoras' theorem to prove it, but the other side is 3. Well, if you're in this quadrant right here, it's positive 3. But if you were to write it on this triangle down here, it's not positive 3. It would have to be negative 3. Does that make sense so far? In a way, what I've got right here is I've got a coordinate point. This coordinate point could be 4 and 3. And it would provide me a triangle in which cosine of theta is 4 over 5, because the adjacent and the hypotenuse are 4 over 5, or the x and the r are 4 over 5. But there is a second coordinate point that would also make this work. If I had the coordinate point for negative 3, it would actually still meet these parameters. Which is why there's this next part right here. What this little part right here does is it restricts the domain. Okay? We've talked about domain at some point before in your courses. Domain is all of the x values you can use, right? Well, in this example right here, it's not x anymore, it's theta, it's the angle. But what I'm going to do is I'm going to restrict your angles. 3 pi over 2 and 2 pi. Basically what I'm telling you is we're only going to look for angles between 3 pi over 2, which is right here, and 2 pi, which is right here. So this little thing right here lets us know which angle to pick, because there's actually 2 that could have worked. We're not taking this one. We want the one that's in these parameters right here. Does that follow? Okay. And the last little thing, and maybe with this example you can kind of see why I had to show you all these little tidbits along the way. Because the last question then is, well, if I asked you what cotan was equal to, that's the last little bit. So now we have to know, well, what is cotan equal to? Well, cotan is what happens when you flip tan. So why don't we start with tan? Isn't tan supposed to be the opposite over the adjacent? Or in our example, y over x? That's what tan is supposed to be. But we weren't asked for tan, we were asked for cotan for whatever reason. So cotan just means to flip it upside down, make it a over o. Or in our example, let's make it our x over our y. So what's our x value? In this quadrant right here, our x value is 4. Our y value was -3. That would be this one here. Yeah, see how that kind of like culminates and kind of comes together now? So this is what we're going to start working towards. Is I'm going to start giving you equations now involving cosine or tan and angles. And this is kind of leading into my last lesson then. We want to now start to be able to solve these sorts of things using all of these like little bitty tidbits of information I've shown you along the way. Okay. Does anybody have any questions up till now? Do you guys have the last set of notes printed off? Okay. So let's go right into our last set of notes here. This is what I've finally been waiting for, okay? Okay. So all of that is finally to get to this moment here. Our goal now is to be able to solve a trig equation. Okay. And again, this is about where the line between where grade 11 math stops and grade 12 math starts. Because for you guys that are in grade 12, everything I just showed you up until now should have more or less been a review. You guys remember doing this a little bit last year? Okay. This is more or less where grade 11 is supposed to now more or less end here in like a slide or two. But if it's okay with you guys in grade 11, I'd like to show you just one more lesson because we've come all this way and shown you all these little random things along the way. And all of those things were to now be for this point. Okay. So here's kind of the conclusion. Do you need to take off? Oh, do I need to have like a brief pause here to get you guys notes done? Okay, why don't I pause the lesson here, print off some notes here. Okay, well, while those guys finish up the notes here, let me just explain to you guys some more of the rationale as to why I'm doing this. Maybe you don't even care, but this is more or less the point where the 20-1 curriculum stops. And I think that it was stupidly designed. I'll even say that out loud. Because if it feels like up till now I just taught you a random mismatch of stuff, I feel that way. And then they're supposed to tell me, stop teaching grade 11. And I find that frustrating because then in grade 12, you're supposed to have relearned, you're supposed to have known all this stuff already, but it feels like we didn't really accomplish a whole lot. Does that make sense? Like, do you guys feel like I do right now where it's like, we didn't really do anything? Like, I showed you a whole bunch of stuff about how to plot angles and plot them on grids and find points and stuff like that, but like, what do I do with it? Is that fair to say? I don't know. Hopefully you feel that way. Right now, this is basically the end line. This is where 20-1 then should stop. Okay? But what I found, experience has taught me, is that I need to do a thorough review of it for my kids in grade 12 because they probably don't remember what they learned last year all that well. And I figure while we're here, I'm going to do one more lesson with you guys in 20-1. Okay? So I want to make sure you guys are perfectly clear. This is just slightly beyond your curriculum. Okay? But if you're planning on taking 30-1 next year, I figure it's worth doing it just a little extra. Does that make sense? So that's why I'm doing this. Okay? I'm going to put this question, a few questions of this on your assignments, not on your tests and quizzes. Okay? But I think this still has value to you guys, just so you can kind of see like why I taught you all this random mismatch stuff of cast laws and plotting points and coterminal angles, because hopefully all of that will now summarize in this final lesson. So I think you guys good to go now? Do we have all the stuff we need? We're still not there yet? Did Josh not follow you up? Oh. Okay, well I'm gonna start, and then you guys can fill in a second, okay? So here's kind of the whole point, in my opinion, behind why we learned all that background information. We want to learn how to solve equations. Okay. In the past, you guys should have learned how to solve this example right here. This is a linear example, or a quadratic. Now, depending on whether you're in my -1 or my 30 level class or my 20 level class, you should have learned how to maybe solve an absolute value, or maybe fractions. You guys in 30-1, you've learned how to solve logarithms, and those were lots of fun, right? Well, what we're going to learn today now, with all of the background information I finally taught you, is we're going to learn how to solve sine, cosine, and tan, and be able to do algebra type skills with those as well. Okay, that's my goal now, is building all those together. Okay, so I want to show you that there's two types of solving. If I can go back on a slide right here, let me just start with this one right here. If I were to give you this equation right here, If I told you that x was 1, could you solve for y? Okay. What if I told you that y was 1? Could you solve for x? You get how there's like two types of solving? Sometimes I give you the x value and ask you to solve for y. Sometimes I give you the y value and I ask you to solve for x. Okay. Take the quadratic graph right here. If I told you that x was equal to 5, could you get an answer for y? What if I told you that y was equal to 7? Could you solve that as well? There's like two ways of solving. Well, the same thing applies when you're solving sine, cosine, and tan. So that's what my first slide here is. Let's say that I tell you to solve sine 30 equals x. This is actually really easy. This is basically like you're literally just plugging in a number. You're taking sine of 30 and you're doing like something like this. Got a calculator here. You take sine of 30 and you literally just type in sine of 30. What is it telling you though? When you ask a calculator to type in sine of 30, what does sine of 30 mean? Well, now that I've done some review, isn't sine supposed to be equal to your opposite over your hypotenuse? You guys remember that from a little while ago, right? Sine is equal to opposite over hypotenuse. Well, what it means then is that if I type in sine of 30, any triangle, I'm going to grab a triangle making tool here. Give me a sec. Where's the shape tool? Well, I don't have a triangle making tool anymore. Never mind. If I were to make a triangle, bear with me for a sec here. Here's a triangle. I'm going to make that be 30 degrees right here. If I were to enlarge this triangle and make it bigger, like say by doing that, is the relationship between the opposite and the hypotenuse, has that relationship changed if I make this bigger? Well, no, because if I make it twice as big, then this is twice as big and this is twice as big. But the ratio between sides is still the same. So it doesn't matter whether I have a very, very small triangle that has 30 degrees in the corner or whether they have a very large triangle with 30 degrees in the corner. Sine of 30 degrees, what it means is that the relationship between the opposite and the hypotenuse is 1/2. It means that when your opposite is 1, your hypotenuse is 2. So if this is 1, this is 2. If this is 100, this is 200. Does that make sense? So when you ask a calculator to go sine of a number, what it's really telling you is a relationship between two sides. So when you do sine, you're asking it, well, what's the relationship between the opposite and the hypotenuse? If you're asking something cosine, you're asking it, what's the relationship between the adjacent and the hypotenuse? And if you're asking it for tan, you're asking it for what the relationship is between the opposite and the adjacent. And if you make the triangle bigger or smaller, who cares? Is the relationship between them different? Well, no. Right? If I make the triangle twice as big, or 100 times as big, 100 divided by 200 is still going to be 0.5. Does that make sense? So these ones are really easy to do. Sometimes, though, we'd like to find them in exact values. Like, for example, if I asked you for sine of 60, we've learned in a previous slide way back where I'm not going to find it, but I believe root 60 can be replaced by root 3 over 2. You guys recall that from like one of our earlier lessons? And that's the relationship between sides. If I were to make the triangle bigger, it could be 2 root 3 over 4. Or it could be 200 root 3 over 400, but the ratio is still the same. What I believe my next slide then shows is just that same sort of idea about SOHCAHTOA here. Okay? If you're being asked for sine 30, then all you're getting is the relationship. Okay? What I've got right here is a picture of a trig table. Okay? And literally what this is before we had calculators, and a calculator could do all the math for us with pre-programmed numbers, a trig table would literally tell you what the relationship is between all of these values. So like if I pick a random number, like say 30 degrees right here, the relationship between opposite and hypotenuse, because sine is opposite and hypotenuse, is half. If you ever have an angle of 30 degrees, your opposite is half as big as your hypotenuse. Does that make sense? That's what this table tells you. If you have an angle of 33 degrees, your adjacent compared to your hypotenuse is 0.8660 of whatever your hypotenuse is. So if your hypotenuse is 1,000, your adjacent is 866. You guys follow that logic? And then tan, well, the relationship of tan is how big your opposite is compared to your adjacent. Okay, so it used to be that they actually had these big trig tables, and every time you were looking for an angle in either radians or degrees, you'd have to look up what the ratio is between them. Calculator is now pre-programmed to handle that for us. So let's try some examples here. We're going to find the exact value of some of these angles. And we might only get about this far today. So this is the type where I'm going to give you the input, find the output. So sine of 300, what does it equal? So in order to kind of work with this type of example, why don't we graph it first, which is why I built these first 2 days in, where we just get an idea of, well, what does 300 look like? So trying to figure out, those are question marks, by the way. Where is 300 degrees going to be? In which quadrant? Okay. So I'll put it in this quadrant right here. I'm going to make a reference angle triangle. What angle goes inside the reference angle triangle? Does that make sense to everybody else? I know my grade 12s were saying that out loud. You guys in grade 11, you follow that? Okay. Well, what is sine 300 really asking you for? It's asking you for the relationship between the opposite and the hypotenuse. How big is your opposite compared to your hypotenuse? Which is the biggest side in a triangle, by the way? The hypotenuse. Which means that if the hypotenuse is the biggest side, when you take an opposite and divide by a number that's clearly bigger than this should give us a decimal number, less than 1. Does that make sense? So then we got to try to figure out, well, how can I find the exact value? And this is where those triangles from way back when kind of come in. I'm going to redraw one of them. It was a triangle with 2's on all sides that you then sliced directly in half, which meant that rather than it being 60 degrees, 60 degrees, and 60 degrees, when you cut it in half, there's only 30 degrees left. You guys remember this triangle here? This is, by the way, dash 1. This is 20 level curriculum, by the way. That wasn't something that you weren't supposed to know. Do you guys remember this triangle at all? What's this side right here now then when you cut it in half? And this side over here is root 3. Well, this is a triangle that I can now take and superimpose up here. Because don't I have 60 degrees right here? I just need to know which sides go where. So 60 degrees goes across from root 3. 30 degrees goes across from 1. And the hypotenuse is 2. However, one of those is written wrong. Which makes sense. Because we learned, again, another random little tidbit I threw at you, according to the cast rule, cosine is the only thing positive in this quadrant. But we were asked for sine. So when we find the relationship between the opposite and the hypotenuse, the answer should be negative root 3 over 2. Because the opposite is negative root 3, and the hypotenuse is root 2. So this is our answer. That's a negative root 3 over 2. Now the great news is you can confirm this in your calculator really easily. All you've got to do then is type in sine of 300. You have to make sure that you're in degrees. Okay, that is going to be a relationship. Now right off the bat, it's negative. Is that a good thing? Yeah, we expect it to be negative, right? If I were to then confirm that the exact value is root 3 over 2, hey, it's the same value. So now we know the exact relationship between how big this opposite side is compared to how big this hypotenuse side is. Does that make sense? Okay, let's try another one. I'm going to ask you to solve this equation. I'll even write it a little bit differently here. Why don't I skip down, though? Can I do the... actually, no, we should do this one here. Let's say that I told you that y equaled cosecant of 135 degrees, and I asked you to solve that. Okay, grade 11s, I wouldn't actually ask you this because cosecant is not actually in your curriculum, but we're here. We may as well just do it because it's right there. Okay. First of all, let's start with 135 degrees. Where does 135 degrees get plotted? Second quadrant, right here. Again, this is why I had to kind of start with standard position. What's the reference angle? If this right here is 135 degrees, what's the leftover portion? Sweet. So it's 45 degrees. Nice job. Doing okay. That won't work. I've got a list of the kids who have. I mean, some haven't been here, but these are all of the kids in my advisor group who have finished this.
Okay, cool.
Okay, 45 degrees is one of those triangles, though, that you're supposed to know about. Okay. Again, regardless of grade level, that's the requirement in dash 1, 20, or 30 is that you know that if this side is 1 right here, and this side is 1 right here, this side over here is root 2. You guys remember that? Or if you don't, you're going to learn it as we go along. However, I still have a mistake, though. Yeah, this side right here has to be negative 1 because we're going backwards to make this work. Okay, well, now we have to understand what is a cosecant asking us to do? A cosecant is asking us what the relationship is between two sides. We just need to know which two sides we're talking about. And I mean, feel free, by the way, to go write these down from like a previous set of notes. But a cosecant is asking you, how big is the hypotenuse compared to the opposite? Okay. So a cosecant is how big is the opposite hypotenuse compared to the opposite. So the hypotenuse over the opposite, the hypotenuse is root 2, and the opposite is 1. So the final answer to this should be root 2. This side right here is always going to be root 2 times bigger than this side right here. If I take this triangle and I make it a million times bigger, hopefully I'm making my point here. I'm going to do this in red. If I took this triangle right here and I made it bigger, is the ratio from this side to this side any different? If I make it, well, no, because I've made it the same side bigger on both sides, right? So that's all a cosecant does. It tells you is what the ratio is. Now here's the downside. Is there a button on your calculator for a cosecant? No, but we can be clever. So again, 20s, this isn't actually your curriculum, but we're here. Okay, I may as well show you this. You can't type in cosecant, but you can type in sine. So if you were to type in sine of 135 degrees, and then when you're done, press to the -1. Grade 11s, you guys have previously learned that this -1 button right here means make it a reciprocal. You guys remember doing that? So if you can't do secant, do -1 like this, and it'll give us that number right there. Well, that number right there is root 2. So even though you can't type into your calculator a cosecant button, you can type in sine and then make it go to the -1, and that accounts for the cosecant. Does that make sense? Okay. Let's skip down. We don't need to do all 6. Let's skip down and do D. So this is why I need to show you what radians looks like, because I could ask you to take the secant of 11 pi over 6. So again, this is why we need all that background information, because if you don't know what a secant is, if you don't know what 11 pi over 6 is, like 3 days ago, you guys in grade 11 probably had no idea what this meant. You know what I'm saying here? Like it would have been gibberish, because what the heck is a sec? And why is there pi as part of this, right? But hopefully now you have a little more background information. So the first thing we got to do is figure out what 11 pi over 6 is. Hey. Okay. Okay, sorry guys. Okay, where am I here? We might have to end with this one here. I don't think we'll get much further. Can you guys plot where 11 pi over 6 goes? You already beaten me to this? Hopefully you put it in this quadrant here. Let me show you why in case maybe you didn't intuitively pick up on that. If we're breaking things up into sixths of pi, here's the first sixth of pi. Here's the second sixth of pi. Here's the third sixth of pi. Fourth sixth, fifth sixth. This right here would be the sixth sixth of pi. 6 over 6 is 1 pi. 1 pi is halfway around the circle. Okay, 6 sixths. 7 sixths, 8 sixths, 9 sixths, 10 sixths, 11 sixths, and then all the way back around would be 12 sixths of pi. 12 over 6, though, is 2, which is 2 pi is what a circle is. Why is 2 pi what a circle is? What's the circumference of a circle? 2 pi r. So that explains why we do this. I'm not saying it's fun, but it does. Hopefully it does make sense as to why all the way around the circle is 2 pi worth of fraction. So if you're in agreement that this is where we should be, now we got to figure out what that last little angle there in the corner is. We're probably going to want to convert to degrees. I'm quite experienced because I've got 10 years at doing this on you guys. But even then, I still convert sometimes because my brain does not process radians all that well. So I would convert it unless you have it memorized. So I do something like this. 11 pi over 6. I'm going to times by 360 degrees and divide by 2 pi. And if I do that, I think it's 330. Yeah, 330 degrees. That makes sense to everybody else? So if you can handle that, if it's 330 degrees all the way around this rotation, then the next question is, well, what is the leftover bit left inside here? 30 degrees. Which means this angle over here is 60, and there's a 90 right there. So I'm going to draw in purple here my triangle. I'm going to erase some of the other stuff because it's a little busy in there right now. So this or this. All right. You guys feel comfortable getting the location? Okay. Next thing we got to do, we need to be able to superimpose the sides on here. And again, you need to know, regardless of whether you're in my 11 or 12 class, you're supposed to be able to find out what the sides of a 30, 60, 90 triangle are. So I believe this side right here is 1, this side right here is 2, and this side right here is root 3. But I still made a mistake, though. I need it to be a negative 1. Okay. Technically, that is where the dash 1 curriculum ends in grade 11, in case you care. I think it's stupid because it doesn't make sense to go from there. So I just want to show you one more step if you're at dash 1. If I ask you then to solve something like this, all you have to know then is what a secant is asking you for. A secant is what happens is when you flip a cosine upside down. So if cosine is adjacent over hypotenuse, I'm asking you for hypotenuse over adjacent. All you've got to do now is look at your triangle and figure out what the hypotenuse is, figure out what your adjacent is, and that's what this is equal to. Now we actually have done something purposeful with this math. If I were to ask you to say what y equals secant of 11 pi over 6, you can now tell me that the answer to this is 2 over root 3. Does that make sense? This is a grade 11 curriculum. Grade 12 curriculum just says, take it one step further. You guys see why I'm just doing this while we're here? Hopefully that makes sense. Okay, one last thought here, and then we'll call her a day. Yeah, we'll call it a day after this example. I'm going to finish this, and then I'm going to show you what we're going to do tomorrow, and then we'll call it a day. Okay, there's no button on your calculator for typing in secant, which is fine. You don't need one. all you got to do is type in cosine of 11 pi over 6. If you didn't notice while Charlie was doing announcements, I quickly flipped my calculator to radians. You got to make sure you're in radians. I'm going to type in cosine of 11 pi over 6, but I'm going to make it go to the minus 1. This will account for it needing to be a secant. It's going to give me that value right there. This is the relationship between hypotenuse and adjacent. Your hypotenuse is always going to be 1.15 times bigger than your adjacent. But if I want to get that as this value right here, the exact value, I'll just do 2 divided by root 3. And you'll see it's the exact same thing. So your hypotenuse is always this much bigger than your adjacent. That's what we just learned. One last thought, then we'll call it a day. There are always two ways of solving things, though. When you're solving, I could give you the x value, you tell me y. Okay. But I could give you the y value, and you tell me x. This is what I'm going to show you tomorrow, where basically the idea here, if I can find an example here, is what if I tell you that sine of theta equals 0.5, and I ask you, find me the angle. What we're going to discover tomorrow is that this is very challenging because there's actually more than one right answer. Okay. So why don't we leave it here, and then this is what we'll pick up with tomorrow. Does that make sense? I should be able to finish this by the end of tomorrow, and then next week I'm going to give you a whole week to work, okay? Because you guys need some work time, some time to try this now. That make sense? Okay, you guys can take off. We'll talk to you later.